Okay, so yesterday we started studying an example, and in fact this example combines pretty much everything we saw since the beginning of the semester. So I think even though it's a very simple problem, it is very useful in the sense that we get to see how what we have seen before becomes useful when working on a real world problem. So this is a very nice problem, a very nice example in that sense. Okay, so we started with a car, and the goal is to control the speed of the car. So we wrote a very simple equation for this car. Obviously this simplifies the problem a lot, but nevertheless it's very useful in the sense that it is a good enough model for the actual speed control of a car. Okay, so we started with this block diagram. In this block diagram, our car is represented with this block, and then what enters as input to this block is the force. Okay, so the net force acting on the car enters this block, while excluding the road friction. The road friction is included here already. So the force is composed of the force provided by the engine of the car minus a disturbance force. Okay, so and then there's a second block, and this block is used to model the engine of the car. The output of this block is the force, and the input is the gas pedal position. Okay, so this is our initial block diagram. This was our initial block diagram. And then for this we used we both considered a static engine model, where the engine model transfer function is just a constant number, and then we also considered a dynamic first order engine model. Okay, then by using this model we made some simulations in MATLAB, and also by using the analysis tools we saw earlier, we also plotted the speed of the car when we apply a step input to the gas pedal. Okay, so we saw that if you apply a step gas pedal input to the car starts accelerating and it reaches a constant speed. And how fast it reaches this constant speed is quantified in terms of this tau parameter, which we call the time constant. So if time constant is a small number, then the car reaches quickly, or if it's a small number, then that means the car will accelerate at a slower rate. Then we considered the control problem. And in that case, we said, okay, what if we want to reach a certain speed? And let's say we want to drive at a constant speed of 25 meters per second, and then what should be the gas pedal input for that? Okay, so to answer this question, we use the steady state values of the output. Bu section bayağı verimli çıktı ya. Geçen section'a göre bir anda. Yani neredeyse biraz daha beklesek sınıfta olacak. So, in our previous analysis, we saw that if we apply a step input, step gas pedal input, the car eventually reaches a steady speed of this much. Okay, so by using just this part of the equation, we said, if this is the gas pedal input, which causes this steady state speed, then if I want to reach a certain steady state speed, I can solve what should be the magnitude of step gas pedal input I should apply to the car. And that number gives us this, right? So if I want to drive at 25 meters per second, I should put that number into this equation, and that will give me, I should apply a gas pedal input of 1/2, which means half of the maximum gas pedal we can apply. Okay, so this is a control strategy, in fact. So this control strategy is plotted here. Okay, so the car is here. Input to the car is the force, and the force is the net force, which is the total force of the engine force and the disturbance force. The engine force comes from the engine. This is my engine block. Input to the engine block is the gas pedal position. And I just found the gas pedal position magnitude by using this relation. Okay, so this is a step command. So this is the unit step input. So I should write here unit step input. And the magnitude of this step is determined by this number. Okay, and the desired speed becomes important here. So this is where I have the desired speed input. Okay, and then this gas pedal is applied to the engine, which creates a force, and then the car accelerates, and in the end we get some speed. So we did all of this yesterday. And then yesterday we also did some simulations to see how this works. Okay, if the car model we have is accurate, which means if the actual car is really represented by this transfer function, and if the engine model is also accurate, which means we call this KE actual. If this KE actual number is exactly equal to this KE number here, and on top of all of this, if there is no external force, everything works nicely. So that means if you want to reach 25 meters per second, we precisely reach that speed. So there's no problem. But if these ideal conditions are not satisfied, if this KE actual is different than this KE number, then we saw that we cannot reach our target speed. Okay, so we will arrive at a speed which is different than our target speed. Or if there is a disturbance, then similarly that disturbance will cause the car to go slower or faster, depending on how that disturbance is. If you are climbing uphill, for example, as in this figure, obviously the car will go slower. Or if you are going downhill, then the car will go faster than our intended speed. Okay, so this is not a good thing, right? So if we are designing a controller, ideally we want our system to work as intended, even when there are such unideal situations. So, but in this case, there's nothing we can do, right? So we choose our gas pedal input according to this relation, and this relation doesn't care what the real speed of the car is. So what would a human pilot do? So suppose that you are driving this car and you step on the gas at a certain rate, and then you see that your actual speed is less than your desired speed. So what you do, you obviously step on the gas a little bit more, right? You give more gas to the car. Or if you find out that you're going too fast, your actual speed is greater than your target speed, then you slow down, which means you give less gas pedal input to the engine. So that's what should a controller do. Obviously, that's obviously the thing to do. So how much gas pedal applied should be decided based on the actual speed. Okay, so to be able to do that, we make a control loop, a controller, or a block diagram, I should say. We should use a block diagram that looks like this. Okay, so this is our target speed, okay? And we should compare the real speed of the car with this target speed by taking the difference. So we take the speed of the car, bring it here, and then take the difference between our desired speed and the actual speed. So this now becomes the error in our speed. Okay? So now, obviously, if this is a positive number, that means the actual speed is less than the desired speed. In that case, we should apply more gas. So based on this error, we can decide what to do. Okay. Now this is the error signal, and we need to decide how much gas pedal input should be applied to the car. So this is the actual input to the car. So now I'm enlarging the block diagram, if you notice that. So the original block diagram is here. So when we first started studying the problem, this was the original block diagram, right? So the original block diagram is right here. So the input to this original system was the gas pedal input, but now the gas pedal input is here. So I'm making the block diagram larger, and this gas pedal input should be determined based on the speed error, and that should be accomplished by another system which we call the controller. Okay, so now we put this block in the block diagram to complete the block diagram, and this system takes the error in our output as input and then decides how much input should be applied to the system and gives it as the output. Okay, so in this sense, this block is a system itself, right? So there's an input to this block and then there's an output to the block. So this works as a system, and hence we call controllers as control systems. So that's why the word system is used to define control systems. Okay, now this control strategy, in total we expect this to work much better than the previous, because now the controller knows if you're going faster or slower. Okay, so this is a very critical information, and by making clever use of this information, we can make the control performance much better. Okay, let's see. So I don't know if you can read this, but it says here, we feed the output back to form the error signal, and this creates a loop in the block diagram. Hence, this control strategy is called closed loop control or feedback control. It's talking about this loop here. So we feed this signal back here, and this creates a feedback loop. So this control strategy is called closed loop control or feedback control, whereas the previous one is called open loop. So there's no loop here, there's no loop connection. This is called open loop. Okay, so let me just type here. Okay, that's open loop control. Okay, now this is something we put ourselves, right? This is not a part of the car itself. It is just some system, some block we introduced to the system, and we choose what to put here. So when everything is linear, car is a linear system, and hence it has a transfer function, we call that G. The engine is approximated by a linear system. In fact, we used a constant gain for this, so this is a linear static system. So the easiest thing to do is to choose the controller as a linear system as well, so that we can obtain a transfer function for everything. And now this is something we need to choose. Okay, so we need to choose a transfer function here, and then by putting this transfer function, hopefully we will get a nice performance between for the speed of the car, speed control of the car. That means whatever speed we want to drive at, we will be able to do that despite all the difficulties, like despite the external disturbance acting on the car, or despite the errors we have in these parameters. Okay, now for a linear system, there is a transfer function that represents this controller, and that transfer function is to be chosen. So the transfer function can be anything. We have a lot of possibilities, right? So we can have, we can choose whatever we want here. We can put like a 10th order transfer function if you want to, but that means we need to choose all those parameters, right? So if you put a 10th order transfer function, it will have a denominator like that, a1 s to the power 9, a2 s to the power 8. So all these coefficients are to be decided. Instead of doing that, let's start with the simplest possible controller. And the simplest possible controller has just one parameter to be chosen, which is just a constant number, k. Okay? So in the simplest possible controller, the control transfer function is just a constant number, k. Okay? Mm-hmm. Well, okay, so maybe I should explain it a little bit more. The controller is a part of the car actually, but is not a part of. It's not what? Okay, so think of it this way. Suppose that you pick up a car, an old car, which doesn't have speed controller. Okay, in that case, to control speed of the car, you need to push on the gas pedal, right? And the driver does that. And if you want to design a control for that car, you need to put like a robot there who will press on the gas pedal, right? And that robot is this controller. So that's what I meant. It's not a part of the car. It's something we add externally to the system. But now most new cars have such speed controllers, and for those cars it is a part of the system already. Okay, so as I said, let's start with the simplest possible controller, which is just a constant number, and see how this works. Okay, and what I mean by that is, if we give the controller a target speed, let's see what the actual speed of the car will be when we put this controller in the block diagram. So to answer this question, we need to simplify this block diagram, right? Because we have now 3 blocks, and to find the effect of applying an input to this system, to see the effect of that input on the output, we need to obtain the transfer function from here to here. Okay, so that's what we should do next. So by the way, by forming this feedback controller, we changed the input to the system, right? If you look at the original block diagram, there were 2 inputs. One was the disturbance force, and the other was the gas pedal input. Now, in this new block diagram, the gas pedal input is now an internal signal and not an external input to the system anymore. And the external inputs are, one of them is still the disturbance force, but the other one is the desired speed. Okay? So we should obtain the transfer functions. Again, there are 2 inputs, the desired and ft, and we should find transfer functions from these inputs to the outputs. Okay? So now we make use of the block diagram operations we saw before. So we can simplify this block diagram to obtain these transfer functions. So for example, you can just multiply these 2 blocks since they are connected in series, and then you will have this summation junction. You can move the summation junction to the other side of the this block to combine it with this summation junction, and you can get the transfer function easily that way. And if you do all of that, these are the transfer functions that you will get. Okay. So the transfer function from the desired speed to the actual speed is given by this relation, and these are the transfer functions of the individual blocks. For example, this G and this G are the same, and they represent the car transfer function. And the GE here, they represent the engine, and GC and GC here are the controller transfer functions, right? So we choose it as a single constant number, but you can put something else there if you want to. Okay, so similarly, the transfer function from the disturbance input to the speed of the car is obtained as this transfer function. Okay. Now, we can, by using these transfer functions, we can calculate how much the speed will change if we apply or if we give a desired speed to our controller. Okay, and to do that, we just need to multiply this with the transfer function of this plug. But before this, we should find the Laplace transform of the input signal. Okay, and by the way, these transfer functions are called the closed loop transfer functions of the system. So this is the transfer function of the car, transfer function of the engine, and transfer function of the controller. But when everything is combined to obtain this function you see here, this new transfer function is called the closed loop transfer function, because we close the loop to obtain that transfer function. Okay? Nasıl gidiyor? İyi miyiz? Ya ben size bakıyorum ama aslında aklımda şey var. Hani burada evinde oturup YouTube'da seyreden insan var. Dolayısıyla siz beni uyarın yani, böyle hani diverge ediyorsam bir yerden. Okay, so this can be simulated. In fact, I want you to do that. Okay, so yesterday I showed some simulations in MATLAB. We used MATLAB LSIM function to simulate the system. So you put a transfer function here, and it calculates you the output by numerically solving it. And for this case, for example, this is what you need to give to MATLAB. So you need to form that and put it here, and the result will give you the performance with the loop closed. So anyway, but before doing simulation, let's take a look at this function and see, for example, how or what the state speed of the car becomes when we use that controller. So when we apply an input here, the output is obtained by multiplying the transfer function with the Laplace transform of the input. So this is the transfer function, by the way. So if you put the transfer functions, all these G, GE and GC into here, and then make the simplifications, in the end you will get this transfer function. So the speed of the car becomes this times the input desired speed. So to see that, let's assume that the desired speed is a constant number, which is very reasonable. So the car is at rest, and then we set the target speed to some constant number, and let that constant number be Vd. Okay, so that means so this desired state speed is a step signal with magnitude Vd, in which case the Laplace transform of that becomes Vd times 1 over s. This is a function of s. Okay, now we take this and multiply it with this transfer function, the closed transfer function, and now this gives us the speed of the car. Okay. So at this point we can find the actual result by taking the inverse Laplace transform of this function, which is not difficult to do, right? For that we need to use partial fraction expansion, or instead of doing that, or we can more quickly calculate the steady state value of the speed, right? And to find the steady state value, we need to apply the final value theorem on this function. So that's the most easy thing to do at this point. So let's do that here. So this is the final value theorem. You take the limit as s goes to 0, and in the limit you put s times v of s. Okay, and the s here cancels this 1 over s in the v of s function. And after the cancellation, and when you put 0 into s here, this is what you get. Okay? In other words, if you use this closed loop controller to control the speed of the car and choose the controller transfer function as a simple number, which is k, and apply a constant input to the controller as desired, then your car will eventually reach a speed of this much. Okay? And as you see, the actual speed depends on the controller parameter. So if you put 0 here, for example, then your actual speed will be 0, which is very reasonable. That means you're not applying any input at all. The car will just sit there. Or if you put a different number, then your actual desired speed will be given by this equation. Okay? Okay, so we still have something like 25 minutes, but this is where I stopped in the other section. So I don't know what we should do here. Well, okay. We will try several things here. We will try different values of k. But I want to point out that if you look at this function, you can easily see that applying a large k value is a good thing, right? And in fact, if you just consider the limit, if you, maybe I can just edit here. From the above equation, we can see that choosing k to be a large number is a very good thing. If you consider the limit, as k goes to infinity, it's just equal to Vd, right? Okay, so this tells us that in the ideal case where infinity is used for the controller transfer function, steady state speed of the car always becomes equal to the desired steady state speed, independent of KE and B. So obviously this is a very good thing, because yesterday we saw that if the engine constant KE is less than the engine constant that we use for the controller, then that directly affected the state speed of the car when we used open loop control. Right? So for example, instead of reaching 25 meters per second, the car only reached a speed of 20 meters per second. But now in closed loop control, we see that if we use infinity for k, then it doesn't get affected by KE at all. I mean, KE can be 10% of the original engine number, or it can be greater than the original engine number. And in all those cases, the car reaches the target speed. Well, obviously, using infinity is not a very realistic case, and we will see why. But for now, I think it's enough to say that at least we can see that if we can choose very large values, then it will be a very good thing. Okay? Hmm?
ilgili konuştuk ya. Şimdi burada kontrolü de var. Farmın bölgesine baktık. Bu transfer function disturbance'ından bağımsız oldu. Yani mesela sürtünmesiz bir ortamda yaparsak açıyı, yani beyaz olacağı için ne kadar bilgi yok tutarsak falan istediğimiz hızla ulaşabiliyor. Yani disturbance'ın bir şey kalmış. Bu gerçekten.
Ya onu sorduğun çok iyi oldu. Okay, so the question is that this result is independent of the disturbance inputs. In fact, we just ignore disturbance to find that result. Obviously, it is still there, so we should do that. So the disturbance is still affecting the speed. So if there is a disturbance, it will be added to the output of this, and then that's what we should do really. So let's do that. We ignore the disturbance force, and let's see what happens when there is disturbance. Okay, in that case we need to calculate this Vs by taking disturbance into account. Okay, now the effect of disturbance can be studied by using this new function we have for the speed. Okay, so since we have time, maybe I can quickly do this. So this G is the transfer function of the car. That was this ms plus b, and the control is just k. Engine is ke, and then I have again bu böyle oldu değil mi? Okay, and now just like what we did yesterday, let's assume that So this is the disturbance force when the car is climbing a hill with this angle. Eksi olması gerekiyor galiba, doğru söylüyorsun. Okay, so this should be negative, right? So that's a very good point. Thank you for correcting that. So we should use a negative sign there, so that this becomes minus. And so is this. Oldu değil mi? Okay, now after all of this, we can write it one more time. Okay, yeah, I think everything is correct. So from here we can see so the actual state speed of the car when there's also disturbance will be given by so let me just write the end result after all the simplifications. Böyle oldu. Yani so if the car is climbing uphill as the disturbance, then that does affect the actual state speed. But it still doesn't change the fact that if you can use infinite k here, then the limit will still be equal to Vd, right? So this will become unimportant. And so that is even for large values. So for finite but large values of k, so the importance of this gets small. And in fact, we will see that through simulation. So for example, in the open loop control, like 20% error in KE causes 20% error in the final speed. But in this case, depending on the value of k, 20% error here can cause an error of like less than 1% if you choose a proper k there. So that means the effect of, even for finite values, if it's large enough, you can make sure that the effect of inclination or the effect of the error in your engine can be made very, very small. And this is with a constant controller k. And if you use a more advanced controller with some transfer function, you can make it even better. Okay? So hopefully you will see all of this in MATLAB when doing these simulations. Okay? Any other questions? Okay, so thanks for coming. Let me stop here and I will see you next week.